Class, in this video, we are going to review the very basics of operations with radicals. And so it's very important as we start this process that we review what is the radical. Well, the radical, here as we think of this little division sign with this squiggly bar. A lot of times I will leave this off, but in your math book you will probably see there's a little clip there on the side. A lot of times I'll leave that off because when I'm writing, you'll see what I just did here. It's separated and it begins to look like the negative, which we can have that, and so that can confuse things. But when we begin to think about operation with the radicals, I think it's helpful to think of fractions. 1/3 plus 2/3. Now we know that that equals 3/3. Now this is just an example, random numbers. But I know that I can add 1/3 and 2/3 because they have the same denominator. And so the denominator stays the same, and then I add 2 plus 1 and get 3. It is a similar process when we deal with operations with radicals. You'll notice that here, the radicand, the number under the radical, is the same. That means that I am able to actually execute the math operation. So in this case, I want you to think of the number outside the radical, in this case a 3, and in this case a -4. Treat it like you would the 1 and the 2 when adding fractions. These fractions have the same denominator. They have a common denominator. These two radicals have the same radicand. That means I can add or subtract. And so to do that, let's go all the way over here. This would be 3 minus 4, which is -1. So -1 times then √6. So your answer would be -√6. So again, you can see why I leave that little clip off the left-hand side, because sometimes I need to exaggerate and demonstrate that there is in fact a negative outside the radical. So when we subtract 4√6 from 3√6, that is -√6. In a case, let me just give you another example. If we had something like 3√6 plus 2√5, well, there's your answer. Because the radicals, the radicand, I should say, the number under the radical, they are different. Okay, and so we're not going to worry about trying to make them the same. Like in fractions, you would get a common denominator. So the illustration there begins to break away, not work, but here this would be in a fully simplified form. And you'll actually see that show up in some of the problems that we do in class. You'll probably see it in this video as well. Let's go back to our next example. You'll notice here, and I would encourage you with just the illustration that I gave, pause the video and go ahead and try to work -3√7 plus 4√7 and see if you get the correct answer. All right, so hopefully you've done that. You'll notice that the radicand is the same. It is 7. That means I can take the number outside the radical and do the math operation. In this case, it's -3 plus 4, and we know that is 1. So your answer is √7. That would actually be your simplified final answer. Let's go down and look at a couple of more examples. Here we have 2√6 minus 2√24. Now, if you think about the first two examples, you're tempted to say, well, 6 and 24, those are different. So obviously that must be the simplified form, but that would be incorrect. Now, when we think of 6, we know it has factors of 1, 2, and 3, but none of those are perfect squares. And so being that none of them are perfect squares, I'm going to leave this one alone. And so sometimes you'll see me do it this way. I'm going to just drop it straight down. 2√6, that tells me that there's nothing else that I can do there. But 24 is different. 24 has at least one perfect square in it. So I'm going to have 2√6 minus 2√4 times √6. Now elsewhere we have reviewed simplifying fractions, but we know here that if I multiply √4, now we're not adding, subtracting, I'm multiplying, that means I multiply the numbers under the radical. And I know 4 times 6 is 24. So now I have simplified √24 into √4 times √6. Now why would I do that? Go ahead and bring this down. 2 root 6 minus 2. Square root of 4 is a perfect square. And so now we can begin to see how this simplifies. 2 root 6 minus 4 root 6. Now the number under the radicand, they are the same now. And so 2 minus 4 is negative 2. So that is going to be negative 2 root 6 will be your final answer. I would encourage you to pause the video at this point and try our next example, 3 root 18 minus 2 root 2. All right, well, now that you've attempted the problem, we know that 2 is a prime number, so 2 root 2, that's going to stay just the way it is. 2 root 2, there's nothing I can do. But when I see 18, and this is where knowing your multiplication facts is so important, because I know immediately that 2 factors of 18 are 9 and 2. And I also know my perfect squares. So 9 is a perfect square. So this will actually simplify to 3 times root 9 times root 2. Make sure that's a multiplication dot, not a subtraction sign. So as I continue to move down, that's negative 2 root 2. This will become 3 times root 2. And now we can just move across. That's going to be 9 root 2 minus 2 root 2. The radical is the same now. 9 minus 2 is 7. So my answer is 7 root 2. Let's look at one more example. Oh, wow, this one gets a little more difficult, but not really. I've just added one more term in there. And so let's begin to look at this. I would encourage you to pause the video at this point and attempt this problem on your own. Again, it's just one more term. Well, we start off, we know that 2 is a prime number, so this is going to be negative 3 root 2. Nothing's going to change there. Plus, the 20, I know my factors of 20. 2 of them are 4 and 5. 4 is a perfect square. So this becomes 3 times root 4 times, let's erase that. Something went crazy there. Let's try that again. Times root 5. Now I know 4 times 5 is 20. They're both under the radical, so that reduces back to 3 root 20. Just trying to work backwards to reiterate why I've written it the way I have. I'm looking for this perfect square right there. Now, I also know the 2 of my factors of 8 are 4 and 2. So 3 root 8 becomes 3 times root 4 times root 2. Now, you'll notice that I wrote the perfect square to the left. And the reason I do that is because as I bring this down, negative 3 root 2 plus 3 times, I don't know, pen must be going bad, 3 times 2 root 4 becomes 2. Now I have the radical already shifted to the right. So I've gotten my terms organized in such a way that's very, very helpful. It just kind of seems more seamless that way. Root 4 becomes 2, and that's going to be root 2. So if I were to take, and you don't have to draw all my arrows, but hopefully it helps, negative 3 root 2 plus 6, 3 times 2 is 6, root 5 minus 6 root 2. Now, let's look carefully at this. Here I have negative 3 root 2, and I have a negative 6 root 2, but look in the middle. That's a plus 6 root 5. So I'm going to combine like terms essentially here. Negative 3 minus 6 is negative 9 root 2 plus 6 root 5. The radicands are different, and there's nothing else I can do. Negative 9 root 2 plus 6 root 5 is this equation simplified. All right, class, I hope this helps. There's definitely a lot we can do with this. There's plenty more examples to be worked, but let me know if you have any questions.